And notice this R. The R has a subscript S now. Didn't have no subscript here. Now it does. Why? Because that's radius is the Schwarzkopf radius, right? Or Schwarzschild radius. So that means that it's a black hole. You know what I mean? Right? That's the Schwarzkopf radius is the radius you'd have to have for some mass for it to turn into a black hole, right? So now we take that, we multiply both sides by R subscript S, right? And we get this. Now we can do two things with this formula, right? We can either get the radius, right, the distance, or we can get the mass. And you can see over here, all you have to do is, if you want mass, divide this by 2g. And you'll end up with these two formulas here, right? And you can see that if we use the mass formula, right, and we plug in c squared, this is our Planck, right, our Planck length, right? We'll put a Planck length for R, or for our Schwarzschild radius, right? And then we divide by big G, right? And here's big G, right? You can see the unit, the 10 to the powers I did over here. 35 plus 16 is negative 19, and then you minus this, which will make that a positive, so it make negative 8. And then I took these two numbers times each other and divided by that using a calculator. Here are the units, right? The M3 and the M2, and you know, you got 3 on top and 3 on bottom. They get out of there. Second squared, they get out of there. You're left with kilograms. Now, for some reason they didn't use this number 2. The only way this works out, right, because they use, remember, they use this other formula to get all these Planck lengths. They only use G, Planck's constant reduced, and the speed of light, right? They only use those 3 constants to get these numbers, right? So we're using real formulas here, you know, and when you leave the 2 out, you get exactly this. And this is exactly what he has, right? So if you do have a mass, right, this mass, and you have it in this small of a distance, you know, you have a radius is this, right? Look at what happens. I don't know why they took the 2 out of the equation. I mean, it doesn't work out unless you use that 2, but if you don't use that 2, you will get this, right? For 10, you'll get the same exact answer as him. If you use the 2, right, you will still get 10 to the negative 8th kilograms. It's just you're going to be off by a little bit. You're going to have 1.089 instead of 2.176. Okay. Now, this is just an FYI off of the side thing. Okay, this has nothing to do with anything, what I'm going to say next. But this big G is actually incorporated, if you look over here with these, right, with the force, the gravitational constant formula for force, or whatever this is called, you can see that they took out the 4 pi and incorporated it into this reduced G, and that's what we use. We don't we don't call it the reduced G, but that's actually the reduced G, right? Now, if you were supposed to use the regular G, right, it doesn't have this 4 pi incorporated, then you'd have to use this formula. And this is the kilograms that you would get, which is 10 to the minus 10. I don't think this is right, okay? What I think is this G, it should actually be the real G, but you should also have the 4 pi here right before the R. So it doesn't really make a difference, okay? I don't know which is right and which is wrong. I think that this is right up here, okay? Because you're supposed to leave that 4 pi in there into this formula, right? You're not supposed to take it out like over here, okay? But either way, you can see he is correct. Planck is correct that you will get a black hole, right, at 10 to the negative 8th kilograms, right? And what about the energy? Does this energy correlate to a black hole? Well, here we have E equals mc squared, right? We got that mass, right, that we had up here that he says, and we multiply it by c squared, and here is c squared. We get this, and then we get this. Here are the units. They come out to kilogram meter squared per second squared, because you're taking mass, kilograms, right, times c squared. That's meters per second, and each one of those are squared. But if you put them together, look, it's kilogram meter squared per second squared, which is a joule, which is 10 to the 9th power. And what does he have? He's 10 to the 9th power, 1.956, 1.956. So yes, at a, so basically, right, let's do this last formula, right? Obviously, distance per time is velocity, meters per second. If you rearrange that, you'd have distance per velocity tells you the time, right? So if I put the distance, which is the Planck length, and I divide it by the velocity, which is c, right? Because you're going at the speed of c, and then you get your time. And this 5.39 times 10 to the negative 44, 10 to the negative 44. You can see all of these things correlate to something. All four of these, length, mass, energy, time, but they don't correlate to the smallest unit that can be, okay? What they correlate to is the smallest unit that you can take a picture of, because once you get down to this thing here, you're smaller and smaller, your sine wave gets more compressed and more compressed. You make a black hole at this point, okay? And that's all it's saying. It's not saying anything else other than that. If you say that it says anything else other than that, you're attaching your emotions onto it. All this is saying is you can't take a picture of stuff this small, because if you try to, you'll make a black hole. Doesn't mean that the physics is different below this length. Doesn't mean that there's nothing there, or physics changed. No, your ability to see changed, and you can't see it, so don't attach magic to it, okay? So now let's see what a real, because this is the Planck length if you consider the length that you can't see below, okay? But there is a Planck length that's where these units are the lowest they can be, okay? And let's see how we can figure that out, okay? All right, this is my rant, all right? I start with energy, right? You can see right here, John Black, Planck energy is 6.626 times 10 to the negative 34 joules, which is kind of like H, right? Why do I say this? Why do I say this is the lowest, smallest energy? Because it's one cycle. This is one cycle, right? What does what does Planck's constant say, right? It says you get this amount of joules for every cycle, right, in a second. So if you have this, and this is a second, this is a second, this is a second, how many cycles do you have? One cycle. So you have 1 H of energy. Here you have 2 cycles, so you have 2 H. Twice as much energy. Here you have 1, 2, 3. 3 cycles, you get 3 H of energy. But you can't, no matter what size this sine wave is, right? Whether it's this size, this size, this size, it always gets the same amount of energy. 6.626 times 10 to the negative 34th joules for each sine wave. This is the Planck, this is the lowest energy that you can get as a photon, right? Is 6.626 times 10 to the negative 34 joules, right? And what's the, this is their equation that approves it, right? Over here, right? E squared, that's the electron, that'd be coulombs, divided by 2a, that's the fine structure, E naught C, okay? I don't like this equation, okay? I like these two equations, right? This equation here is more representative of what's happening, and this is definitely more representative of what's happening. Let's look at this, because putting a C in your equation is idiotic. You're just trying to cover up what the C represents, and the C represents this. mu naught square root and over E naught square root. That's what E naught C represents, okay? And then Z naught 0, impedance, that is a ratio of these two things, okay? This equals that. You can see down here, Z, I rearranged this formula, right? So the Z is on one side. It equals 2 fine structure H over E squared. It also equals this, mu naught over E naught, but they're both square rooted, equals Z. Why do I think that this equation is better, even though they're all three of these equations are the same exact equation? Why do I like this equation better? But I want you to see how I take it from here to here, from here to here, and now look at this, okay? What does this formula remind you of? Probably nothing, because it doesn't look like much, right? But what does it look like to me? It looks like this over here. Resistance equals watts over squared amps. You might say that doesn't look like that. First of all, this ZO, it has the ohms for the unit, or the thing that represents them is ohms, just like ohms over here, right? And look at this, E squared, that's close to amps squared, right? But if I take this E squared and I turn it into A squared second squared, right? Now there's my A squared. I mean my amp squared. And I got my ohms over here, right? You might say, well, where's the watts? Well, I can make this, right, joule seconds. I can put the joule there and put the second down here. Why? Because one of these will cancel out. This one on top will cancel out, and this square thing will cancel out, and you'll have a second on the bottom. What is joule per second? It's watts. So I replace that with watts. Watts per amp squared equals ohms, or resistance. See that? How this is the formula. It's an electrician thing. This is your resistor, your amps, and your watts. You got to play with the units, though. If you don't play with the units, you never whatever. So you can see why I'm saying that this is the lowest energy you could have, because that's what one sine wave is. You can't have a half a sine wave. You can't have a quarter of a sine wave. You can only have a sine wave, okay? And that sine wave, whether it's this big, this big, this big, it always adds up to 6.626 times 10 to the negative 34th joules per cycle, okay? So I want to find out how much these things weigh. Right? What's the equivalent in grams, kilograms, I mean, of this energy, right? Because that will be the Planck mass, right? So I take Planck mass, right? How do I find that? I take Planck's constant, the energy, right? And I multiply it by E naught, mu naught, right? Permittivity and permeability of space. Here's the, me putting it in, right? This first number is H. Next one is E. Next one is mu naught, or whatever. I do the math, right? I get this, 7.37 times 10 to the negative 51s. Here's the units, right? This E naught and mu naught come out to second squared over meter squared. This over here is the H, right? Everything cancels out, and you end up with kilograms second per cycle. And that is what John Black's Planck mass is, okay? It's this. It's a kilogram second per cycle. And you might say, well, what the heck is a kilogram second per cycle? It's the same thing as a joule second per cycle. It's the same exact thing. You just like over here, what did you do? You took a 1 second, right? 1 second. And every cycle you got this number amount of joules for every cycle, right? Every one of these cycles here, every one of these cycles here, all these cycles, right? So you got 1H joules here because you got one cycle. Here you got 2 cycles in the second. That's 2H joules. Here you got